Hello everybody, welcome back after the break. Today we're going to take a look at a type of problem that you can use differential equations to solve. So let's see here. A block of wood is floating in water. It is depressed slightly and then released to oscillate up and down. Show that the period of the motion, neglecting friction, is 2 pi square root h over g. Okay, so let's look at this here. So yeah, this is what we're showing. We're showing that the period is 2 pi square root of h over g. So this is how things are defined. This is when it's at rest. There's a certain weight down on it, and there's a certain force up on it, which is the buoyant force. And when it's at rest, the block is sitting h units below the surface of the water. The block is also L units tall. And then when somebody comes along and pushes it down, the difference between H and where the bottom of the block is this fancy letter D. We're going to be using the letter D for at least one other thing in this problem. So I'm going to always write it fancy when I mean the displacement, which is why it's named D for displacement. So another thing to consider is that our x starts at the surface of the water and goes down. So this is a positive displacement here, even though it is going downward. So that is something to keep in mind throughout this problem. So the first thing we're going to do to solve this problem is we're going to look at what this h actually is in terms of the properties of water and the block here. So when this is stable and not moving, not oscillating up or down, that means that our weight is equal to our force up on it. So our weight, our W here, is going to be equal to it's equal to the mass of the block times gravity. What is the mass of our block? It's the density times the volume. We're going to break it down one step further though. It is the height of the box times the area of the bottom of the box, which we don't know anything about the height, and we don't know anything about the area of the bottom of the box, but it's fine because we don't end up needing that for anything. The density of our block, rho b, rho block, and times g. And so what is the force up on our block? Keep in mind, this is a positive force, even though it's pointing downward. You don't often have weights that are positive, but hey, what do you know? This is a weird problem. Or at least I'm solving it weird. Take your pick as to what the right answer is. Okay, so our force is upward, but it's negative, and it's equal to the weight of the displaced water. So what amount of water is displaced? Well, yeah, it's the mass of the water displaced times g. We'll skip that step this time. It's the amount of water that's displaced is the area of the bottom of the box times our h. So it's h a rho water, density of water, g. Also keep in mind this is negative. So I guess in this sense, it's not where these are equal, but it's where they are offsetting. So it sums to 0. So let's go ahead and set them equal to each other. So LA rho B G equals HA rho W G. So the area of the bottom of the box, there are a couple assumptions in this problem. Mainly, the box has flat sides, which constantly remain flat, and it has a flat bottom that always remains parallel to the water's surface. Those are important assumptions. The math wouldn't work out nicely if those assumptions did not hold, though it could provide an approximate solution. So the areas are the same. The gravity is the same. We are assuming that we are on a large enough planet that the height difference does not make a difference between the top of the block and the surface. If you have a really large block or a really small planet, maybe double check. And then finally, we get our h is equal to our height of our box, rho box, over rho water, which makes sense. So essentially, the ratio between the height of the box and the height under the water is equal to the ratio of the weight of the water to the weight of the box. Double check if I said that right. I think I did. So it's kind of handy if you see something that's sticking out of the water and you see that like you know 10% of it is underneath the water, you know that it's 10 times lighter than the water. And so that makes sense. We'll be using this a little bit later. And now for the differential equations part of this, we're going to use Newton's laws of motion to describe how this box is going to do its thing. So our force. So yes, the other thing about this problem, we're going to assume that since there's zero force here, we are going to treat the added buoyant force or the lack of buoyant force as positive or negative force. We're not going to add it to the weight each time. We're just going to say we're going to work with the displacement from the steady state and do it that way. That makes this problem a whole lot easier. You could do it the other way and you could get the right answer, but it is much more complex, and this is a much easier way to do it. So we are assuming that this is a steady state and we are going to work with displacements from that. Okay, so once again, our force is the same. We're going to box this off here just so we don't get confused. The force is still here, underneath here. But the excess force, or the lack of excess force, is negative, instead of h, it's negative fancy d, negative displacement area rho water g. That is the amount of water that is displaced from this section of, of the box. And since displacement, it can be positive or negative, it's not just a distance, it's displacement. If it was up, we would have a negative displacement, which would mean a positive net force back down. And then so this is the only force that is acting on this box in the way what we're setting our 0 points and such. So we all know F equals ma. So this is the formula that is going to provide us with our differential equation. Here's where we use our other d's that we're going to be using. And yes, this gets complicated or confusing. So the second derivative of our displacement, because with respect to time, which is just the acceleration of our box, is equal to our force over the mass of our box. And we already found these out. So negative displacement area rho water g. And the mass of our box, if you remember, we figured that out above. L a rho box. So once again, can cross off our A's. And then let's see what we have here. So yes, the x direction is pointing down. Yeah, okay. So we are going to rewrite this and put everything on the same side of the equation, because then it'll be in an easier form for us to solve with what we've learned about differential equations so far. Yes, plus, I'm going to rewrite this very slightly. Actually, if you notice here, we have L row box over row water, and then we have L row box underneath row water. So we're just going to go ahead and replace that now with an H. Remember that it is underneath, though. So G over H, and then R D. So notice that there's two variables, there's two D's here. And this is going to equal 0. So if we rewrite this in terms that we normally see it in a differential equations, a differential equation, we have our differential operator, D, well, let me rewrite that, make it a little neater, D squared plus G over H D equals 0. And what we're going to do is we are going to use the method that we use to solve these second order from the square here, the second order differential equation, we solve it by changing it into a quadratic equation, and then when we get the roots of that, where this holds true as a quadratic equation, when we find the roots, we put it back in to the original equation as an exponential, which is weird, but consult your differential equations textbook for a thorough explanation of why that works. So we are going to do that here. So in a in a quadratic equation, our A, B, and C are, typically are ax squared plus bx plus c equals 0. Our A is going to be 1. A equals 1. We don't have any D's, big D's. We don't have any big D's. So B equals 0. And then our last part of our thing is C equals G over H. So when we put this into the quadratic formula, which if you remember, I'm going to start writing it over here. Oops. Negative b plus minus b squared minus 4ac all over 2a. When we plug in all of these, all of the values that we have, we end up with plus minus negative 4 times g over h all over 2, which we can further rewrite. This 2 cancels with the 4 underneath the square root, and the negative inside the square root comes out as a I. Imaginary number, yes. Square root of g over h. And so these are the roots of our, this is called the characteristic equation, this here. This describes how it works, how the differential equation works. So, now that we have the roots of our characteristic equation, we put it back in as exponential. And if you will remember, when we have complex roots, in this case we have imaginary roots, they go in as it's a complex conjugate pair because it's positive and negative, and we don't have any real part of this. So it will end up being a combination of sine and cosine. And yes. So we will put it back into our equation now. I guess we're using the variable d. D as a function of time, because time is our variable here, is equal to, we don't have a real part of the solution. It's all imaginary, so we don't have to deal with that. We will go C1 as our arbitrary constant, the first one. And that is going to be C1 sine of, and then our root here. Because we're putting it in sine and cosine form, we don't need to keep the I. I'm skipping the exponential step and going straight to the sine and cosine step. So it's going to be square root of g over h, and that is times t, plus our second arbitrary constant, cosine of g over h times t. Okay, so this is the answer, not the answer to the question specifically because it wants to know the period, but this is actually the equation that describes the motion of the box. And notice that this is independent of starting conditions. Whatever the starting conditions are, it will follow something of this form where the starting conditions determine C1 and C2. Now, of course, the last step showing that the period is not much more difficult. It's just so sine, for sine, the period is 2 pi. For sine of 2t, t is equal to pi, because if you think about it, it's cycling twice as fast. So instead of cycling 2 pi, it cycles pi. So by the exact same logic, so notice how even when we multiplied t, there should be a t in there, but when we multiply t by a number, we divide by that for the period. So by the same logic here, also remember we're starting out at 2 pi, sine of square root g over h t. For that, the period is equal to 2 pi divided by square root of g over h, which is equal to 2 pi times the square root of h over g. And this is what the real answer to the question is. You also could have figured this out from this step here if you wanted to, without writing down the entire formula, but I think it's pretty instructive to write down the entire formula. Like for example, if you were to hold the box down for a period of time and then release it, your equation is going to be mostly cosine, or it's going to be mostly or all cosine, depending on how you let go of the box. Or if you shove the box down from its resting position, it's going to be all or mostly sine. But you can play with that all you want. Thanks for watching. If you have any questions, please post in the comments, and see you next time.